All right, good afternoon, everyone. Thank you so much for joining us at the CGD seminar special tea time edition to accommodate our speaker being on the other side of the planet. So before we get started, as people file in, I'll remind everyone of our CGD code of conduct at these seminars, where we encourage innovation, show appreciation for others' work, consider new ideas, offer constructive feedback, share the air and hear all the voices that we have, and acknowledge the teamwork that goes into these efforts. And with that, now it's my pleasure to introduce today's speaker. Paige Martin is a postdoctoral fellow at Australian National University and at the Lamont Doherty Earth Observatory at Columbia University. She received a bachelor's from Harvard and a PhD from the University of Michigan, where she was an NSF Graduate Research Fellow and a fellow at the Woods Hole GFD program. Her areas of interest and expertise include air-sea coupling, climate modeling, high-performance computing, and open source software. Today, she'll be speaking about drivers of atmospheric and ocean surface temperature variance and the Coastal Ocean and Environment Summer School in Ghana. So Paige, you can take it away and go ahead and share your screen.
All right. Thank you so much. Okay, hopefully that is working. Thanks for that introduction. I'm very pleased to be giving this seminar today. I'd like to be able to actually visit NCAR in person someday, but I'm currently stuck in Australia, as Dan mentioned. So I will be talking about kind of two separate things today, because it sounds like there's interest for both. So first, I'll talk a bit about some of the research I've been doing over the past couple of years on temperature variance, and then I'll talk about a summer school in Ghana. And actually, my talk is going to have three parts. Because I'm giving this talk at NCAR, I wanted to include a middle section on some preliminary results of what I've been doing recently that involves temperature variance on CESM. But for now, I will start by talking about temperature variance in the frequency domain in an idealized model. And this work has been published in Journal of Climate earlier this year. And I did the work with my PhD advisor, Brian Arbick, and with my kind of co-advisor here at Australian National University, Andy Hogg. So the motivation, how we kind of started this work, actually stemmed first from some work that myself and others in my lab were doing on energy budgets, also in the spectral domain. And we were really looking at the time at cascades of energy across scales, which is somewhat well known to probably many of you. This was particularly done in the wave number domain, so across spatial scales by people like Salmon and Sheng and Hayashi, some kind of seminal papers. And then more recently, some people in my group, as well as a few others, were looking across timescales. And that was in the energy budget. And we decided we were going to apply a similar method, but to the temperature variance budget. And that's because we are very interested in kind of getting more into air-sea interactions, so right at the interface of the ocean and the atmosphere. So there's kind of this classical view. I think we all know that the ocean and atmosphere have preferred timescales. Going back to Bjerknes and Hasselmann, and there's this kind of idea that the ocean, which moves much slower than the atmosphere, integrates the atmospheric high frequency forcing. Recently, there's been a lot of interest in not just looking at kind of ocean versus atmosphere, but looking specifically at the different mechanisms that are driving the air-sea coupling. And there have been several studies recently that have looked, especially using upper ocean heat budgets by Justin Small and others, and Martha Buckley and several others as well. And here we're not using upper ocean heat budgets, but we're using a temperature variance budget. So we're looking at temperature variability via the temperature variance specifically. And so we'll be looking at all of these different mechanisms that feed into the surface temperature variance budget. So we'll be looking at advection, heat fluxes at the interface, Ekman processes, and we have a model that resolves ocean eddies. So we'll be looking at the effect of geostrophic eddies as well. All right, so our goal, as I've mentioned, is to determine the mechanisms and their associated timescales by looking in the frequency domain, of what's driving surface temperature variance in both the ocean and the atmosphere. And we do this by computing the variance budgets. We also will be looking across different configurations of this idealized model. And we'll be looking in a frequency domain, so we'll be looking specifically at different time scales. So the model that I use to do this work is called the quasi-geostrophic coupled model. It is, or QGCM, as I'll refer to it. It has this, it's very idealized, and that has a square ocean that's meant to mimic the North Atlantic, and that lies beneath this reentrant channel atmosphere. And here's a schematic of it showing the 3 layers in the vertical in each fluid. And it is very idealized, as we can see, but it's actually, it's got some rich dynamics. So it's kind of this nice in-between medium complexity model, because it still has these mixed layers that embedded into both the surface of the ocean and the atmosphere. And that's what allows for the coupling between the 2 fluids. So it's a fully coupled model. The resolution is 5 kilometers in the ocean, so it resolves ocean mesoscales, and it's 80 kilometers in the atmosphere. Notably, there are no seasons, so we get rid of any seasonality, and we're just looking at kind of the inherent variability. From here on out, when I talk about the atmosphere, I'm just going to talk about the portion of the atmosphere that lies in the square just above the ocean, and that's because I'm interested in the air-sea interaction. So I'm not going to pay attention to the rest of this atmospheric channel. And finally, we run the model for 400 years total, but we split it up into 7 overlapping 100-year windows. So the largest time scale that we will see is 100 years, and then we average over those 7 windows in the plots that I'll show you. And you'll see that I show a confidence interval as well on those plots. So I mentioned that I'm using different configurations of this model. So there are 3 configurations that we use. The first is the fully coupled, the FC, and that is defined by these ocean mixed layer velocities. So we have U and V, the zonal and meridional velocities in the mixed layer, and they are made up of a sum of the geostrophic term, which is this pressure gradient, and an Ekman term. We can see over here in the bottom right, this is a snapshot in the color of the sea surface temperature SST, and we can see that it's a very eddying field. The partially coupled, or PC, is the exact same as everything I just said in the fully coupled, with the only difference that we get rid of the geostrophic component of the mixed layer velocities. So what that means is that the ocean still has ocean mesoscales, but that information is not passed into the ocean mixed layer and thus not passed onto the atmosphere. So it's kind of a way of seeing how much the ocean mesoscales affect the mixed layer and then affect the atmosphere above it. And if we look at the bottom right here, we can see that basically all of the eddies are gone because we don't have the mesoscales getting through to the surface fields. And finally, we do an atmosphere only. So we just run the atmosphere and we use a climatological SST. So to compute the temperature variance budget, we first start with the temperature tendency equations. So this is a time derivative of the atmospheric mixed layer temperature. So in the next few slides, I'll be showing a few equations, and I'll go through them pretty quickly, but I think it's important to show. We've got horizontal and vertical advection. We've got these radiative terms. We have sensible latent heat flux. We have this layer 1 heat flux. That's what I'm calling it. It's kind of at the top of the mixed layer in the atmosphere. And we have diffusion. And in the ocean, we have very similar terms as well. With, instead of the layer 1 heat flux, we have this entrainment heat flux, which is due to the Ekman pumping going into the ocean mixed layer. And to calculate the variance budgets, we multiply each of these equations by twice the mixed layer temperature. So then we end up having this 2 times temperature, time derivative of temperature, which is equivalent to the time derivative of the temperature squared, or the temperature variance. That gives us a time derivative of a conserved quantity. And so if we integrate over the domain, we get a closed budget. And we do all of this actually in the frequency domain. So each of these steps mentioned here, we actually convert into the frequency domain by taking Fourier transforms. And this gives us these equations. So you'll notice that's a double integral over the X and Y domain. In the ocean, it's a closed budget. So I say zero, I set it equal to 0. But in the atmosphere, because I'm only looking at the portion of the atmosphere over the ocean, it's actually not a full domain integral. So I don't have it equal to 0 here. But we have all of the same terms as we did previously. And we can see that the terms, so the RE means real part. The hat means Fourier transform, and the star is a complex conjugate. So we have these cross-spectral terms where we have a product of the Fourier transform terms. And what this variance budgets are really great at doing is that they reveal the terms that are adding or removing variance. So we'll be able to tell which terms are kind of driving or damping variance in the system. And because it's in the frequency space, we can look very easily at timescales. So I'm very interested, as Dan mentioned, in kind of the software and computing side of things. So I always like to mention a bit about that. So everything that I'll be showing from here on out was computed on Australia's NCI, National Computing Infrastructure. And I use lots of Python. It's all in Python, and I use lots of these open source packages. I use Jupyter Notebooks and many that might look familiar to you here. So I will start by showing the temperature spectra. So this is essentially showing the power spectrum of temperature. So it's like the kind of total temperature variance. And I have ocean on the left and atmosphere on the right, and they're both log scales. If we look at the ocean, we see that we have this red spectrum, which is what we expect. If we compare the blue, which is the fully coupled, to the red or pink, which is partially coupled, we see that the fully coupled has a lot more variance at the high frequencies or the shorter timescales, which implies that the ocean mesoscale is very important for driving variance in these shorter timescales. In the atmosphere, we have a similar red spectrum, except for this green curve, which is the atmosphere only. So this really shows that ocean dynamics are very important for the low frequency atmospheric variability. Okay, now I will show you kind of first how we're going to interpret the budget terms that I'll be showing in the next few slides. So the temperature variance budget terms can be positive or negative, unlike the spectra that I just showed. So it'll still be on the x-axis, we'll have frequency, so high frequencies or shorter timescales are on the right, low frequencies, longer timescales on the left. If it's positive, if the term is positive, then that's when we say it's adding or driving variance in the system. If it's negative, then it's removing or it's damping variance. And if we have a second term, like this green one, we can compare their relative magnitudes. So the green one is driving, is a larger driver of variance than the red. And here, because the red is negative, we say green is the only driver of variance. So that's just kind of how to interpret these plots coming up. So now I'll show the full budget for the ocean fully coupled on top and partially coupled on the bottom. Note that the y-axes here are different scales. And we can see all of the terms that are contributing here that we saw in the equations before. Because I don't have much time in this talk, I'm just going to focus on the two that are the main drivers at the low frequencies. And that's what I'll talk about today in the talk. So the two main drivers at the low frequencies in both cases are this blue and red curve, and the blue is the horizontal advection of temperature, and the red is the entrainment heat flux, which is due to Ekman pumping. I will note that there's a very big difference that you can see here in the higher frequencies, where the partially coupled, the one without the ocean geostrophy, has very little variance. And so we really see that the ocean mesoscale is important for driving variance at the shorter timescales. So now that we've seen which terms are contributing kind of at the lower frequencies, or roughly kind of 2 to 100 years, we want to get a kind of a better understanding of what these terms are doing. And so instead of just integrating over space like we've done here, I can instead make spatial maps and plot them over different averaged frequency bands. So the top row here is the same term that we just saw, the entrainment heat flux, for the fully coupled on the left and the partially coupled on the right. And then these plots here are showing the spatial distribution of those terms averaged over different frequency bands. So this one here is 2 to 100 years, and we've got 6 months to 1 year below it. And those averaged bands are highlighted up above, so you can see the integrated behavior. So first, we can see that in this fully coupled on the left, we have this purple highlighted region where it's negative before it crosses to being positive. And we can see now where that stems from. So this is like what I'll call the Western Boundary Current WBC region. So it's kind of like the Gulf Stream-like region in this idealized model. And we can see that that is what's driving the damping of variance in this purple highlighted region. And that actually it continues to remove variance in the lower frequency band, but we have this large input of variance kind of further along the atmospheric storm track, really. And in the partially coupled, we don't have any of that variance damping. We don't have any of that negative pattern at all. And so we can see that it's not getting the information from the ocean mesoscale, but it still has this very large input at low frequencies. Because it's along the atmospheric storm track and present in both scenarios, we consider this to be an atmospherically driven input of variance. And because it's in the entrainment heat flux term, it's fueled by Ekman pumping. So we see that one of the main drivers of low frequency variance in the ocean is an atmospherically driven term via the Ekman pumping. So now I'll jump to the atmosphere. And here we have 3 runs. We've got the fully coupled on top, the partially coupled in the middle, and atmosphere only at the bottom. And note that here they all do have the same Y scale. And so we see that in the fully coupled and also in the partially coupled, the main driver of variance is this yellow term, which is the radiative heat. But in the fully coupled, we also have some variance being driven by the blue, which is the horizontal advection. So these are the 2 kind of driving terms in the fully coupled model. And if, again, we look at the spatial patterns, so we do the same thing that we did previously, where the top row shows the integrated terms. And here I'm just showing the lowest frequency band. And we've got horizontal advection on the left and radiative heat on the right. And in each case, the left column is fully coupled, the middle is partially coupled, and the right is atmosphere only. So first, I'll mention that we can see in the fully coupled versions, we can see that there's some behavior due to ocean eddies. So we do see a signature from the Western Boundary Current in the atmosphere at these lower frequencies. So that's the first thing to note. But if we look at the pattern of variability across these 2 terms, we can see that in both cases, the fully coupled and partially coupled have very similar patterns. But those patterns differ greatly from the atmosphere only. So while we have a magnitude difference that's noticeable between the fully coupled and partially coupled, the main pattern stays the same, but not in the atmosphere only. So in the fully coupled, we've got the full effect of the ocean geostrophy as well as Ekman in the fully coupled. Partially coupled, we don't have the geostrophy, but we're still getting that same pattern set up. But in the atmosphere, we don't have even the ocean Ekman terms. And so we claim that the pattern that we're seeing here is likely due to the ocean's Ekman advection. So hopefully I didn't lose everyone in that bit of the talk. So overall, we've shown that the temperature variance budgets, I think, are quite an interesting tool for studying air-sea coupling and looking at specific mechanisms responsible for driving variance. And mainly what we saw is that there's this low frequency ocean atmosphere coupling at greater than 2 years. So the low frequencies in the study that are driven by Ekman processes. So in the atmosphere, we just saw that the pattern was set up by the ocean's Ekman advection. And in the ocean, we saw that it was Ekman pumping that was playing a big role in driving the ocean variance. And we also looked a bit at the ocean eddies and that they are playing a noticeable role pretty much locally in the western boundary current, but in both the ocean as well as the atmosphere, which is quite interesting. So that's just kind of one part of the story that we tell in this paper, if you're interested, and that was published in Journal of Climate earlier this year. So from here, I will jump to the second part of the talk. And this is some preliminary results of what I've been working on. So I do apologize that some of the plots are still not polished, but I thought it'd be interesting to talk to all of you who are much more experts on the topic of CESM than I am, because I've just started working with it. Now I'll talk about basically applying the exact same technique, but to terms in the CESM model. And this work I'm still doing with Brian and Andy, but also with my postdoc advisor, Ryan Abernathy at Lamont. So here I'll be comparing two versions of the NCAR model. So first is the high resolution, which is a 10th degree ocean and a 1/4 degree atmosphere. And we have 40 years of daily model output for the surface fields. And we split that into 7 10-year overlapping windows. So we can only go out to 10 years in this study. And we also look at a low resolution version of the model, which has a 1 degree ocean and a 1/2 degree atmosphere. It actually has a much longer time span, or it was run for much longer, but to compare it to the high resolution, I'm only using 40 years, and we're doing the same 7 10-year windows. So I'm applying the same budget or the same method before that I mentioned, so I'm not going to go through the math behind that here. Here we're looking at the budget over the top 5 meters. So I'm only using surface fields. So I'm not even doing kind of an integral over any sort of depth. And I'm just approximating the surface temperature to be the temperature across the top 5 meters of the ocean. And I'm also only looking at the ocean at this point. Haven't looked at the atmosphere. And I can only compute 3 terms from the output of the model. And that's the horizontal advection, which from here on out, I'll just be calling advection, surface heat fluxes, and then the biharmonic diffusion. But in this talk, I'm mostly going to show just the first 2, horizontal advection and surface heat fluxes. Although we are able to infer a residual, which would include all of the vertical motions, like vertical advection, vertical mixing. All right, so now I am working on the Pangeo Cloud, which many of you may have heard of. I'm personally using Google Cloud. It's really handy. So it basically just opens up a Jupyter hub on Google Cloud. And through Pangeo, it sets up the environment for me. And it gives me access to a bunch of data sets that are already on the cloud through the Pangeo project. And so the high resolution was already on the cloud. So that was really nice. I was able to dive in pretty quickly. But through this analysis, when I decided I wanted to compare it to a lower resolution, we actually uploaded the lower resolution one to the Pangeo Cloud using Pangeo Forge. And that was done just a few weeks ago, actually. And so we now have the low resolution also on the Pangeo Cloud. And I'm still using a lot of these open source packages, and I've actually contributed to a couple of them, which has been kind of fun. All right, so first I'm going to show the temperature spectra again to kind of get a sense of what the temperature variability looks like. So this is the globally integrated plot. Again, it's on a log-log scale. And we have low resolution in blue and high resolution in orange. And so what we can see is that the high resolution has more variance at the kind of sub-annual scales, which given that it resolves ocean eddies, then we can assume that the ocean eddies are contributing a lot to the variance at these higher frequencies. It actually has a similar magnitude up at the lower frequencies, the longer timescales. So we can look at all of the spatial patterns here, like we did with the idealized model. So in the left column here is the low resolution, and the right column is the high resolution. So here I'm going to have to apologize that these are not polished plots, and so they're plotted on slightly different projections. Just remember that when we're comparing across the two, but we can still kind of get a sense of what's going on. And what we can really see is that although it's a similar magnitude at the low frequencies, we can see that the pattern here, oh yeah, I should also mention that I do 5 different frequency bands that are labeled here, and those correspond to the gray and white highlighted regions here. So at the slowest frequency band, we can see that all of the variance is really focused right at the equator in the low resolution, whereas we do see the equatorial dynamics quite noticeably in the high resolution, but it looks to be on par with all of the western boundary currents. So we're seeing a very different pattern emerge across the two. I also note that all of these are in different color bars, so we can see the different patterns. And so we can see here that actually this is even of greater variance, greater magnitude here in the lower resolution compared to higher resolution. If we look at the shorter timescales, we can see that, again, really in all of the timescales for the high resolution, we're seeing the western boundary currents pop out. They're really the major regions of interest. We do see some of this kind of Pacific equatorial dynamics popping out in some of the frequency bands, but not nearly as much as what we see in the low resolution. So we can see that the equatorial dynamics are kind of overemphasized in the low resolution compared to the high resolution, and the high resolution really emphasizes those western boundary currents. And interestingly, the annual cycle or the seasonal cycle looks very similar actually across the two, and of similar magnitude as well, as we can see here. So that's the total variance. Let's look at a few of the terms in the budget. So first we'll look at advection variance. So this is the horizontal advection contribution to surface temperature variance. Again, the low resolution is in blue and the high resolution is in orange. And we're seeing kind of a similar story as what we just saw, that they both are overall globally integrated, are adding variance to the system mostly, but the high resolution is adding much more variance. And again, we see a very similar magnitude at low frequencies. And again, if we look over at the maps, we see that it's this, it's all in the equatorial dynamics in the low resolution, and it's mostly in the western boundary currents as well as the equatorial region in the high resolution. If we look at the shorter timescales, again, it's the western boundary currents popping out in the high resolution. We do see that the low resolution does show some similar behavior where we can see some of the boundary currents adding variance in these frequency bands. But again, we have this kind of overestimate of the equatorial dynamics compared to the high resolution. And this annual scale is actually, we see that there's a difference in sign. So the low resolution overall adds variance, but the high resolution actually removes variance at the annual scale. And we can see that it's stemming mostly from these boundary currents, which are largely negative. We have a bit of this dipole kind of behavior going on that we don't really see on the low resolution. Again, these are very preliminary. I actually don't really know what's going on there. So there's still a lot to understand. And finally, we'll look at the surface heat flux. So this is, again, blue shows the low resolution and orange shows the high resolution. And here we actually get quite different behavior. So except at the very shortest timescales and longest timescales, we actually get a flip in the sign between the two terms, where low resolution the surface heat fluxes are adding variance to the system until we get to the lowest frequencies. Whereas in the high resolution, it adds variance at the very shortest time scales, but then removes throughout the rest of the time scale, annual cycle accepted. So we have the same story if we look at the low frequency band up here. Equatorial dynamics are overemphasized. And here in the high resolution, we mostly see the boundary currents. If we look at the higher frequencies, what we see is that it's these Western boundary currents that are really popping out in the high resolution and that are removing variance very systematically, except at the seasonal cycle, they're all removing variance, which is not what we see in the low resolution. We kind of start to see it potentially in this frequency band, but particularly at these higher frequencies, we're really getting a very different picture between the two. And in this case, each row has the same color bars as well, as they are similar enough. So I think there's a really interesting story there that we'll be digging into. The annual cycle looks actually very similar across the two. So we've got some kind of interesting behavior going on annual cycles. So I don't really have, I guess, a lot of kind of conclusions yet from what I've just shown. So these are just kind of preliminary observations. But we do see that when ocean mesoscales are resolved, that they increase the total variance at the subannual scales. We find that the role of equatorial dynamics in driving variance is really overemphasized in the low resolution compared to the high resolution, which is really dominated by Western boundary currents. And we see that there's kind of an interesting story with a seasonal cycle where sometimes they look very similar across the two and sometimes they look very different. So most of this is to say that we have some kind of interesting results. I'd love to hear any kind of feedback from any of you if you see patterns that look familiar from working with these models. Yeah, I would love to hear that. Looks like we have a question. Are we doing questions now or at the end?
We can take a question now if it's a clarification question. Otherwise, yeah, Justin, go ahead.
Oh, sorry. Paige, thank you very much for the talk. This is Justin, and thank you for using the high resolution CSM. And the what I thought was in your annual cycle results, you found the advection variance change sign, and then the surface heat flux variance looked the same. Yeah. So does that mean that the residual, which is the vertical processes, are playing a role as well? Because you didn't show the residual, but in order, and also when you looked at the total variance, they were very similar.
Yes. Yeah. So I haven't computed the diffusion term, which is the other one I could compute for the low resolution yet. So I didn't show that here. But what I did find in the high resolution is that the diffusion term plays a very small role until the very highest frequencies. So exactly, I would expect that the residual would balance out this difference, that we'd see a flip in the sign in the residual from the vertical motions as well.
Okay. All right. Thank you.
Yeah. All right. So that's everything that I had to say about kind of the science side of things. So again, very happy to take questions after this talk or by email later or anything. But now I will talk about the third aspect of this talk, which is very different from the first two. And this is COSSING. So this is Coastal Ocean Environment Summer School in Ghana. I'm going to call it COSSING from here on out. It's quite a mouthful. So when it first started in pre-pandemic times, it took place in the country of Ghana, which is in West Africa. And the school took place in Accra, which is the capital city. The goal of the school was to build capacity in ocean and environmental sciences in Ghana, but also in kind of West Africa in general. The school has been held yearly since 2015, and it was held in person in Ghana until 2019. And then due to COVID-19, was moved virtual in 2020 and 2021, just a few weeks ago. And the in-person schools alternated hosts between the Regional Maritime University and the University of Ghana, both based in Accra. And the school, when it was in person, it was a one-week school, and the only cost for attendees was travel to Accra. The registration, the housing, and the food during the week of the school was provided free of charge to everyone. And at the end of the week, certificates were awarded, as you can see in this picture here, and everyone got a photo of receiving their certificate. Instructors have come from US, Ghanaian, and European institutions. There were about, I think, like 10 to 15 instructors for the in-person schools, and many more for the virtuals. We were able to accommodate people from different places. There are roughly 100 to 150 participants in the school. That is especially true for the in-person schools, a bit higher for the virtual ones, but the participation was kind of at different levels, of course, in the virtual school. Participants mostly come from Ghana and Nigeria, as well as several other West African countries. And now that we've expanded to go virtual, we've been getting more countries in other parts of Africa and actually throughout the world, including Kenya, India, and Malaysia, just to name a few. And the participants come from a range of different career stages. So we can see here that this was in 2020, that more than half are students, undergrad and grad students, but we've also got a sizable fraction of postdocs and research scientists, faculty, other ocean professionals, and as well as other category, which I believe includes a few government workers. The structure of the school, when it was in person, we had morning lectures and afternoon labs, which included computational and fluid labs. There's a field trip. This was always a highlight of the week, in my opinion. We took a field trip to the Tema port in Accra. And we also went to a nearby beach and lagoon and would do some kind of fluid lab activities there. In 2018 and 2019, we added a component where we had small group research projects, and that was really tailored to the more advanced attendees, so faculty or advanced graduate students, things like that. And there they worked together with one or two instructors and then presented kind of the results of their research over those few days at the end of the week. Virtually, we had to change the structure, unsurprisingly. And so it was really based more on, we had some synchronous events, but we had a lot of material that the participants could read or could watch on their own time. So this included pre-recorded lectures, which are now on YouTube, and they're freely available. We did a lot of panel discussions. This was something we added in the virtual school, and these were done synchronously via Zoom. And here's one example of those, where in 2020, we did a Pathways Through STEM panel. We had a number of computational and fluid labs. I'll talk a bit more about computational labs because that's what I've been involved with. And those were all meant to be able to, you could walk yourself through them. And then participants could join these synchronous tutorial and office hour sessions that were held on Zoom as well as Slack to ask questions and to go through some of the concepts in those materials. So as I mentioned, in addition to being one of the main organizers of the school for the last couple of years, I have run the Python computing aspect of the school. So because it's something that I'm quite passionate about, you'll hear a bit about this in the next few slides. I think it's kind of interesting looking at the kind of history of the school. So it started in 2015. My first time was actually in 2017. But the first 3 years were they used MATLAB for the computational labs. That was simply because the instructors knew MATLAB, so that made sense. When we came to 2018, it actually wasn't until we arrived at the school that we realized that we weren't going to be able to rely entirely on MATLAB. And that's because we were able to use MATLAB in the school computer labs, but participants didn't have it on their own computers and couldn't access it because it's proprietary software. So I will note that I really have nothing against MATLAB, but we really realized that we had to use something that was more available to the participants. And because I have been using Python, I was the instructor that knew Python, and we kind of decided to do our best. And we introduced Python specifically for these research project groups. And it was a big success. And we then decided that instead of teaching proprietary software that participants really didn't have access to except during the week of the school, that we would teach Python from there on out. And we converted the school to Python. So there are different ways that you can use Python. Mostly we've been using Anaconda, which is a Python distribution. So you can download it and install it on your local computer. In 2020, we introduced another option, which is using Google Colab, which is through Google Cloud. So you can actually get free Google Cloud computing resources. Now you can't do very large computations, but for many of our small labs, this was more than sufficient. And so this was providing an option where I didn't have to do quite as much setup. So the downloading and installing was often a challenge, and virtually I was worried about helping people with that step. So that was the option there. This past year, we decided to go with our own Jupyter Hub setup. So we went through a company called 2i2c, which is kind of spawned out of the Pangeo community. And 2i2c was able to set up basically a Pangeo Cloud like Jupyter Hub for us. And there were a lot of benefits to this. So similar to Colab, there's no setup needed for participants. So here, all they do is they can log in with their login credentials, and they can just open up any Jupyter notebook that's here and just start running it. So that was really great. For me, trying to manage everything, it was really nice that everyone had the same Python environment. And one really big benefit is that we had access to all of the data sets that are on the Pangeo Cloud. So that was really great. We ended up doing some analysis on Echo this year. And because whereas Colab, we had some restrictions on computing resources before I had to start paying, here we were able to easily scale up computing power thanks to some generous donations through the Pangeo community. And we had one lab where we were able to scale up a DAS cluster and do some computations on some Echo data sets. So the main downside, there are probably other downsides, but the main one that I noticed is that there's a need for stable internet access, which I think is easier to, my take from talking to the participants is that the stable internet access is actually more doable than large bandwidth internet access. And you don't need large bandwidth for this because all of the computation is in the cloud. So I think that's a real benefit of cloud computing. But as I mentioned, that Anaconda is still kind of, a lot of participants really preferred kind of downloading to their own computers. So I think it was enough of a success from what I've kind of garnered from the people who participated this past year that we're planning to continue this in the future. And we will see how it goes. So my primary goal in teaching these and kind of leading the Python computing labs is to make sure that attendees know that Python is available as a free and open source tool. There's, in a 1-week school, it's very hard to teach a lot, especially when Python is just one of many topics at the school. But what we've seen is that just introducing and getting participants started with Python and with Jupyter and these other packages, that they've been able to take that and learn on their own and really kind of take it running. And I'll show an example of that on the next slide. One of our participants who's really used Python in his career now. And especially, I guess, before this year, trying to get everything installed onto people's computers and just comfortable using Python and Jupyter, I think is really important. Here's a list of some of the labs that we've had in the last few years. So notice this past year, we added Intro to Cloud Computing and Echo data analysis, as I mentioned before. So now I'd like to just briefly mention kind of one of our participants named Mubin Oladipo. He's a PhD student at the University of Ilorin and an assistant lecturer at Kola Daisy University, both in Nigeria. And he was a participant in one of the research groups in 2018 when we first introduced Python. And I asked him for some feedback, and he sent this. He said, Python is versatile, robust, and a very good tool. Being open source, it is a leverage for researchers like me in a developing country where access to research grants is limited. I've implemented energy-saving instrumentation for tracking solar flares using Python with a computer and a Raspberry Pi. I also use Python for my data visualization, data analysis, and data presentation. Python has greatly improved my research capability. So when he mentioned this, I kind of asked him for a follow-up, and I said, well, what do you mean this instrumentation for tracking solar flares? That sounds really interesting. So then he responded and kind of told this story. So he said that instrumentation is a challenge in developing countries because of poor power supply, technical know-how, and lack of access to these components. And so the research is being impeded by these factors. He was able to construct a very low frequency receiver to collect data for his PhD work. And it actually was Python that helped him do this, but not kind of directly in the programming side. He said, hitherto, I was using a desktop for the data collection, but the desktop consumes about 300 watts, which was beyond my budget for power backup. Consequently, the Raspberry Pi, which is a small computer, setup solves the problem of power. It consumes less than 10 watts. Therefore, our budget on power backup was sufficient and the project was a success. So basically here, once he learned Python, which is an actual programming language that he could use to program a Raspberry Pi, he was able to use a Raspberry Pi, which is much more efficient in its power usage instead of a desktop. And then he was able to set up this instrumentation in an affordable way. So I just thought this was a really amazing story about how important it is that we're teaching really transferable and versatile open tools. All right, so that's all I have to say about COSSING. If you want more information, you can go to our website. You can follow us on Twitter. And before I end, I wanted to mention this concept of ocean core, which I'm involved in. This is something we have applied to for endorsement through the UN Decade of the Ocean. And the idea is that we'll start something like a Peace Corps, but for ocean science. And this is building off of the success of COSSING. So, maybe we'd be starting more summer schools that are similar to COSSING, but Ocean Core is kind of a much larger in scale and concept. So it will go beyond just summer schools, but all different international collaborations and really how we can, work as a global community of ocean scientists. So we're still in the early stages and kind of forming Ocean Core and how we will move forward. But if you want more information, you can go to globaloceancore.org. So with that, I'd like to thank you for inviting me to present today. And I will leave you with this photo of a sea eagle catching some prey from the ocean, which I took a couple months ago on my newfound photography hobby here in Australia. So yeah, thank you very much.
Great. Thank you so much, Paige, for an exciting look at both your research and your international education activities. We've got some time now for questions, so folks should feel free to raise your hand or enter some questions in the chat, and I will read them. Okay, I see a question from Yiming. Go ahead.
Yeah, thank you. Yeah, very nice talk. Thanks for sharing the story of Python teaching the last. It's really meaningful. Yeah, for the science part, I'm really interested in your variance budget analysis, especially for doing it on the Spectra space. So I have a quick question about the advection variance spectrum you showed in part 2. So do you know why the high-res model has a more smooth spectra in the high frequency band compared to the low-res model? Yeah, it seems the orange line is quite smooth here.
Yes, I probably do. It's probably because they're different, because the resolution is different. We have more points that we're integrating over in the high resolution. So my guess is it's simply because I guess except for this dip here, which I admit I actually don't know what this what this is. I haven't investigated that yet, but this behavior here, I think is mostly due to integrating over a smaller number of points. So it's less smooth. The other thing is that you'll notice that these plots, I don't think I actually mentioned this, are symmetric log, but right around 0, I have to indicate a linear, a place where it goes linear. And so some of this may be because it's in a linear scale, kind of within these 2 gray lines. So those are my guesses for that.
Okay, thank you.
That makes sense.
Yeah, it makes sense. Yeah, and by the way, for information, I have been doing a very similar work about computing the temperature variance budgets. Yeah, but what I used was a forced ocean model of the POP model, not coupled one. And in that simulation, all heat budget terms, including the vertical advection mixing, were saved. So if you are interested, I'm happy to share some of our results and chat more on this topic sometime later.
That would be great. I'd love that.
Yeah, thank you.
Yeah, thanks.
Isla, go ahead.
Yeah, thanks for the talk. I was also interested in your variance budget. I was wondering if you had to worry at all about covariability between the terms, like if you have one term that's big, but it's always opposed by another one, or is it always, was the interpretation kind of always clear?
So I think basically we're like when we have, it's kind of a cross spectrum that we compute. And we didn't really look at kind of within that, the different terms, we just computed them and are interpreting it kind of as a whole. I'm not sure if I quite understand your question, sorry.
Yeah, it's something I have been struggling with, is like, if you know, attributing the variance to terms when they were kind of all balancing or opposing one another. And I was just wondering if somehow your method was kind of, that was built in that you were dealing with that, but maybe I'll check out your paper.
Yeah, I see. I think, so we're interpreting kind of each term as we're computing it. So here, you know, advection, we've included kind of all horizontal advection. In our residual, which I haven't plotted here, but a residual in the CESM case would have, you know, vertical advection, vertical mixing, for instance. But in that case, we can't tease them apart because we haven't been able to isolate, or we can't isolate those 2 terms. So in that case, we wouldn't be able to tease apart whether they're, we can say the whole residual looks like this, but we can't figure out which one, you know, if there's a lot of kind of opposing behavior, we wouldn't be able to figure that out. So yeah, we're really basing on just the terms that we have in the equation.
Okay, thank you.
All right. I had a question about the variance transfer between atmosphere and ocean, a couple of cases in the first part of the talk.
Mm-hmm.
Do you find that that's mostly linear, or that's, I guess with the role of eddies, is that still just, you know, that, you know, variance is linearly translated between the domains, or are there nonlinear effects there too?
I think probably mostly nonlinear, I guess, depending on the terms. So the advection is definitely due to kind of, it is a nonlinear term. So yeah, I guess we didn't specifically look at linearity, but the terms themselves, like nonlinear, the advection is inherently a nonlinear term. So yeah, I actually think we've mostly attributed this to, I guess, nonlinear behavior, particularly since we have, in our temperature variance budget, we have a product of 2 terms. So it's kind of a nonlinear method.
And I guess, does that result in, you know, so you have timescales of motion in one fluid that are translated into timescales, different timescales in the other?
That's a good question. Yeah, so This method alone, I don't think can quite reveal that between the fluids. What we can say is that if there's like kind of going back to this idea of like a cascade of energy, like in the energy budgets, like I mentioned in the first slide, if we were seeing a cascade within a fluid, we would expect to see, which actually we do see in this entrainment heat flux term and in no other term, we'd expect to see this crossing of the zero line. So in my energy budget paper, we interpreted this crossing of zero where it's removing variance in this case at these higher frequencies and adding that could be an indication that there's, in this case, a forward cascade of variance due to this term. But because we don't see much of this crossing at zero, we kind of went away from this idea of cascade. And so, yeah, and then you're asking across the fluids. And I don't think that this method can quite decipher that.
Okay, thanks, really cool. Peter.
So in the low resolution ocean model, you are partially resolving the Rossby radius near the equator, but not at higher latitudes. And you also have enhanced meridional resolution near the equator. So yes. Isn't that the reason that then the variance is dominated by what's happening at the equator in the low resolution?
So I have, in doing this integral here, I've weighted by the area of the grid cells in the two models. So I believe that we've gotten rid of that kind of meridional like equatorial bias, I guess, whatever you want to call it, in the low resolution. So I don't think that is affecting kind of the magnitudes that we're seeing here. But the resolving of the Rossby radius would probably make a difference. That may be why we're seeing such a difference between the two.
All right. Thank you. Well, not seeing any other questions. Paige, I'd like to thank you again for a very exciting talk, and thank everyone for coming, and we'll see you next week. Take care.
Thank you so much.